Welcome to the deep dive. We are skipping the pleasantries today and jumping straight into architectural mastery. If you've ever had to set up or troubleshoot a software pipeline in GitLab, this is for you. We're going to give you that foundational map for its CI/CD system. We've got a huge stack of material here, and our mission is to basically split this whole architecture into two pieces. Think of it as the instruction manual, which is the brains, and then the workhorse, which is, the engine.
And that separation is so key. I mean, understanding the declarative part versus the execution part, it just helps you escape that CI/CD black box feeling. You can immediately ask, is this a problem with my instructions or is the environment itself broken? And that just cuts your troubleshooting time in half.
Exactly. It's knowing the what versus the where. So let's start with the brain, the instruction manual. That is always the .gitlab-ci.yml file. This is the single source of truth for the entire workflow. But there's a logistical thing that can stop everything before it even starts. Where does this file have to live?
It's the simplest rule, but it's also the most absolute failure point. It must be in the root directory of your repository.
Not in a subfolder.
No nesting, no subdirectories, no exceptions. If it's not there, GitLab just scans, finds nothing, and your pipeline never even starts. It just sits there.
It's like putting the key under the doormat. Has to be in that one spot.
Yeah.
So once GitLab finds it, it starts to parse the structure. You mentioned a hierarchy. What about stages and jobs?
Right. So this hierarchy controls the flow. Stages define the sequential order. Think of them as milestones.
Like build, then test, then deploy.
Exactly. They run one after another. And a stage can't begin until the one before it is completely finished.
And finished successfully, I assume.
Oh, absolutely. If stage one fails, stage two never even gets looked at. Now, jobs are the actual tasks that run inside those stages.
Okay.
And the key insight here is concurrency. Unless you tell it otherwise, all the jobs in the same stage, they run in parallel.
And that's huge for performance tuning, isn't it? If I have, say, 3 different test suites, I can make them 3 jobs in one test stage.
And they'll all run at the same time. You get your results back in, roughly a third of the time. It's where you get that massive time efficiency.
So let's dig into the jobs themselves.
Yeah.
For someone looking at a pipeline they didn't write, what are the 4 must-know keywords they need to spot immediately?
Okay, yeah. Let's focus on the core 4. These probably make up 95% of what you'll see. First, the only mandatory one, script.
The one you can't live without.
You must have it. This is just where you put your shell commands, the npm install, the go build, the actual work.
And if the last command fails?
The job fails.
Yep.
End of story. A non-zero exit code means failure.
Simple. So that's the action.
Mm-hmm.
But the action needs a place to happen, an environment.
Which brings us to image. This keyword defines the base environment, which is almost always a Docker image.
So that's for reproducibility.
Exactly. You specify a Node.js version in your image, and every single time that job runs, it starts in that exact same clean container. No surprises.
I've seen teams skip that and just use whatever's on the runner machine itself. That seems risky.
It's a huge risk for security and consistency. Using a defined image with the Docker executor creates this secure, disposable boundary. You're not touching the host machine.
Okay, so we have script for the what? Image for the where. What's third?
Third is tags. Tags they're often misunderstood. They're not just labels. They are the communication link.
The link between the instructions and the engine.
Precisely. A job uses tags to say what it needs. I need a runner with GPU access, or I need a runner that can deploy to production. Only runners registered with that matching tag can pick it up.
So if I tag a job deployment server east, but no runner has that tag, what happens? Does it fail?
It doesn't fail. It just sits in the queue. Forever. It's perpetually pending, waiting for a compatible engine to show up. That's a super common reason for stuck jobs.
A communication mismatch. Okay, what's the 4th keyword?
The last one is artifacts. So when a job finishes, that clean Docker container we talked about, it disappears.
It's gone.
Vanishes. If that job made anything important, like a compiled binary or a test report, you use artifacts to say, hey, save these files before you disappear.
And you can pass them to the next stage.
Yes. It's how you manage state between these isolated jobs. If you don't declare it as an artifact, it's just garbage collected, gone.
That makes so much sense. Artifacts are just shape management for disposable environments.
That's a great way to put it.
Okay, so we have those 4. Is there maybe one more advanced keyword we should mention? Something that controls when a job runs, not just what it does.
Oh, for sure. That would be the rules keyword. It's the modern way to do it.
More powerful than the old, only and except.
Much more. With rules, you can set up these complex conditions, like only run this job if a certain file changed, or if it's on the main branch.
So you could have a rule that says only run this heavy-duty test if the Docker file was modified.
Exactly. It stops you from running unnecessary jobs on every single commit. It's huge for saving time and, money. It makes the instruction manual smart.
Okay, that's a perfect transition. We've talked about tags being the address. Now let's meet the postman, the workhorse, the GitLab Runner.
This is the software that actually does the work. It pulls GitLab, picks up the jobs, and runs them on your infrastructure.
And when you set one up, the first big decision is about scope, right? Who can use it?
Correct. There are 3 main scopes. The widest one is shared runners. They're managed by the GitLab admin and are available to every single project on the whole instance.
So they're convenient, but probably busy.
Very busy, high usage, low control for you. Then you can narrow it down to group runners. These are available to all the projects inside a specific group.
That's a good middle ground for, say, a whole department that wants to manage its own resources.
Precisely. And then the most isolated, the most secure, is the project runner or specific runner.
Dedicated to just one project.
One single repository. This is what you use for jobs that need, super sensitive secrets or access to special hardware.
So if my job is deploying to production, I should use tags to make sure it only ever runs on a dedicated project runner.
That is the security model in a nutshell. You use scope and tags to enforce that boundary.
Now, a runner is just a program running on a server. But what part of the runner actually creates that pristine Node.js container from the image keyword?
That responsibility falls to the executor. The executor is the method the runner uses to run the job.
And this is where the real isolation happens.
This is it. The 2 most common are the Docker executor and the shell executor. If you use Docker, it spins up a fresh container for the job, runs the script, and then just throws the container away. Perfect isolation.
And if I use the shell executor instead?
That dramatically changes the risk profile. The shell executor runs your scripts directly on the host machine.
Oh, wow. So there's no isolation.
None. It's faster, sure, but if one job installs a bad dependency or messes up a file, the next job running on that machine inherits the problem.
That sounds like a nightmare for shared runners, a complete security and stability nightmare.
It is. You basically have to trust every single line of code running on it. That's why the Docker executor, or maybe the Kubernetes one for huge scale, is the industry standard. The executor is the security boundary.
Okay, let's connect this whole loop then, talk about the gotchas. We have the YAML file and the runner. How do they do that handshake?
It all comes back to that synchronization point we mentioned, the tags. The runner is just constantly asking GitLab, hey, got any jobs for me? I have these tags.
Like security scan and needs copy.
Right. And if a job comes along that needs both of those tags, only a runner registered with both will ever see it. That's the handshake. It prevents an expensive job from running on a cheap machine.
Makes sense. Let's talk failure. GitLab CI is known for being fail fast. What's the default rule there?
The default is extreme quality control. A pipeline fails if a single job fails, period.
Doesn't matter if it was a critical task or just a linter.
Doesn't matter. If your linter job fails, the whole pipeline stops and is marked as failed.
That can be frustrating for, non-essential jobs that might occasionally time out or something but shouldn't block a deployment.
And for that, there is a safety valve.
Right.
It's the allow failure keyword.
Right.
You add allow failure true to a job, and you're telling GitLab, look, if this job fails, that's okay. Mark it as failed, but let the rest of the pipeline keep going.
So the overall pipeline might get a warning status, but it won't be a hard stop.
Exactly. It doesn't halt the flow. But you have to be careful with it.
Now, you mentioned allow failure, but we also talked about rules earlier. Are there other ways to control this flow? Other gotchas?
Oh, yeah, absolutely. Advanced pipelines use rules to explicitly define success and failure conditions. You can have a rule that says, this deploy job can only run if the test stage was 100% successful.
So even if a failed test job had allow failure, true, this rule would still stop the deployment.
It would. You have to explicitly connect those conditions. And look, we have to say it one more time because it trips up everyone at least once.
Let me guess. The YAML file location.
The YAML file location. All of this architectural mastery, the tags, the rules, the executors, it's all useless if GitLab can't find the brain in the first place. Root directory, always.
That is fantastic context.
Yeah.
So we've really covered the full loop here. You should now have that foundational knowledge to look at any GitLab pipeline and just see where the brain ends, the YAML file, and where the body, the runner, and its executor begins. You can look at a job and immediately know if the problem is in the commands, the environment, the resource assignment, or the flow control.
And as you move forward with this and you start building more resilient systems, you have to come back to that choice we just talked about.
Allow failure.
Yeah. Given that the default is to be so strict, it raises a really important question for you to consider. When is using allow failure a genuinely good idea for robustness? Versus when are you just using it to hide a problem?
Like masking unreliable tests or some other technical debt.
Exactly. When is it a feature and when is it a patch? That strategic choice is something for you to explore as you apply all this knowledge.